Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Matrices and Linear Systems under the paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. Firstly, the idea of matrices is introduced and some simple matrices are defined. Next, certain operations on matrices, including matrix multiplication, are introduced. Then, mainly real vector spaces are introduced. Span of a vector, linear independence, dimensions and bases for a vector space are defined. After that, determinants are defined. Simple properties of determinants described, rank of a matrix and inverse of a matrix are discussed in terms of determinants. Linear systems are introduced. The fundamental theorem of linear systems is stated and proved and applied to homogeneous and inhomogeneous systems. Finally, Cramer's rule for solving linear systems in terms of determinants is described. The concept of matrices has become a tool in all branches of mathematics, engineering and sciences, and in general, and physics in particular, In quantum mechanics, one-hole approach given by Heisenberg uses matrix formulation and is often called matrix mechanics. Matrices are essential in the study of linear algebra, vector spaces, linear transformations, etc. A matrix A of size m cross n is a rectangular array of the form A equals Aij, which equals m cross n matrix with the first row elements being A11, A12, A13 and so on. The second row being A21, A22, A23 and so on, and the last row being AM1, AM2, AM3 till AMN. The first index M refers to the row number and the second index N refers to the column number. The elements may be real or complex numbers, operators, or themselves matrices. Now, some special matrices. If the number of rows and columns are equal, the matrix is called a square matrix. If all the elements of a matrix are zero, it is called a null matrix. If all the non-diagonal elements of a square matrix are zero, it is called a diagonal matrix. Further, if all elements along the main diagonal are unity, the matrix is an identity matrix, that is I. Matrices with only one row or only one column are called vectors. A matrix having only one row or column is a row matrix or column matrix. A square matrix is called a triangular matrix if all the elements above the main diagonal or below the main diagonal are zero. Upper triangular matrices are square matrices that can have non-zero entries only on or above the main diagonal. Similarly, lower triangular matrices are the square matrices that can have non-zero entries only on or below the main diagonal. Two matrices A and B are said to be equal if and only if they have the same size and their corresponding elements are all equal. That is, A is equal to B, which implies Aij equals Bij for I taking up the values from 1 to m and j can take up the values from 1 to till n. If A and B are two matrices of the same size, then the sum A plus B is the matrix obtained by adding together the corresponding elements of the two matrices. that is C is equal to A plus B. This implies any element Cij is equal to Aij plus Bij, where I goes from 1 to m and j goes from 1 to n. Matrices of different sizes cannot be added. A number which is real or complex is called a scalar. If A is a matrix and C is a scalar, then the product C times A is obtained by multiplying each element of A by C. That is, matrix C is equal to C times matrix A. Or I can say the matrix element Cij is equal to C times the matrix element Aij, where I goes from 1 to m and j goes from 1 to n. The matrix minus A equals minus 1 into A, and A minus B is actually equal to A plus into minus B. So the matrix Cin is called the scalar matrix. Matrix addition satisfies A plus B is equal to B plus A. Also, the associative law which says A plus B within the brackets plus C is equal to A plus B plus C within the brackets, which equals A plus B plus C. Also, A plus 0 is equal to A, and A plus minus of A is equal to 0. If A is a square matrix, then the sum of all n diagonal elements is called the trace of A. A matrix whose trace is 0 is said to be traceless matrix. Given a matrix A, the matrix obtained by interchanging rows and columns defines the transpose of A. That is, A is equal to Aij, which implies A transpose is equal to elements Aji, or I can say A transpose ijth element of A transpose matrix is equal to jith element of A matrix is equal to Aji. For example, if A is a 3 cross 2 matrix given by the first two elements being 1, 3, the second row being minus 2 and 4, and the last row being 3 and 5, then the transpose of A, At, will be equal to, then the transpose of At will be equal to 2 cross 3 matrix with the first row being 1, minus 2 and 3, and the second row is 3, 4 and 5. If for a given square matrix A transpose is equal to A, the matrix is said to be a symmetric matrix. On the other hand, if A transpose is equal to minus A, the matrix is said to be skew-symmetric or anti-symmetric matrix. Let us now move on to matrix multiplication. Let A is equal to Aij be a matrix of size L cross M, and B is equal to Bij be a matrix of size M cross N. Then the product matrix, which is C is equal to Cij, is a matrix of size L cross N and is given by C is equal to AB, which implies Cij is equal to summation over K going from 1 to M Aik into Bkj, where I take up the values going from 1 to and so on till L, and J takes up the values going from 1 to 3 and so on till N. For matrix multiplication, the number of columns of the first matrix must equal the number of rows of the second matrix. If for a square matrix A square is equal to A, the matrix is said to be idempotent matrix. If the matrix A is idempotent, then so is I minus A. Matrix multiplication is not commutative in general. That is, in general, AB is not equal to B times A. For both the products to exist, L should be equal to N. For the two to be equal, L should equal N and it should be equal to M. Thus, For AB to be equal to B times A, both matrices should be square matrices of the same order. In general, even if A and B are square matrices of the same order, AB is not equal to B times A. For example, let us consider the matrix A to be equal to a 3 cross 3 matrix with the first row being 1, 2, 3, the second row being 2, 1 and minus 2, and third row is 0, 2 and 0. Another matrix B is equal to 3 cross 3 matrix with first row being 2, 2 and 1, second row being 0, 1 and minus 2, and the third row being 1, 2 and 0. Now the AB, another 3 cross 3 matrix where the first row is 5, 10, minus 3, second row is 2, 1, 0 and third row is 0, 2, minus 4. On the other hand, the product BA is equal to a 3 cross 3 matrix with the first row being 4, 8, 2, second row elements will be 2, minus 3, minus 2 and third row being 5, 4, minus 1. This implies AB is not equal to BA. We next take up the linear algebraic systems. The rather strange looking rule for multiplication of two matrices can be explained by its application to linear systems. Look at the following set of two equations in two unknowns. That is, y1 is equal to a11 times x1 plus a12 times x2. y2 is equal to a21 times x1 plus a22 times x2. In matrix form, we can write this transformation as y is equal to a 2 cross 1 matrix with the elements being y1 and y2, which equals a times x and is equal to product of a 2 cross 2 matrix with the first row being a11 and a12, the second row being a21 and a22 into the 2 cross 1 column vector which is x1 and x2, which equals another 2 cross 1 matrix with the first element being a11 x1 plus a12 x2 and the second element being a21 x1 plus a22 x2. Suppose that the x1 x2 system is related to the z1 z2 system by another linear transformation. That is, x is equal to x1 x2, which equals b times z and is equal to a 2 cross 2 matrix B with the first row being b11 b12, second row being b21 b22 into the column matrix with the first element being z1 and second element being z2, which equals again a column matrix with the first element being b11 z1 plus b12 z2 and the second element is b21 z1 plus b22 z2. Let the y1 y2 system be related to the z1 z2 system directly by the linear transformation. Y is equal to C times Z, which equals a 2 cross 2 matrix C multiplied by a column matrix C. That is, the first row of matrix being C11, C12, the second row is C21, C22 into the column matrix Z1, Z2. The product equals a column matrix with the first element being C11, Z1 plus C12, Z2 and second element is C21, Z1 plus C22, Z2. But Y1 is equal to A11, X1 plus A12, X2, which equals A11 into, now substituting the values of X1, X2. So we have Y1 is equal to A11 into B11, Z1 plus B12, Z2 plus A12 into within the brackets B21 Z1 plus B22 Z2, which equals A11 B11 plus A12 B21 into Z1 plus A11 B12 plus A12 into B22 into Z2. Y2 is equal to A21 B11 plus A22 B21 into Z1 plus A21 B12 plus A22 B22 into Z2. On comparing the two expressions for Y1, Y2, we have C11 is equal to A11 B11 plus A12 B21. C12 is equal to A11 B12 plus A12 B22. C21 is equal to A21 B11 plus A22 B21. C22 is equal to A21 B12 plus A22 B22. This implies matrix C is equal to the product of matrix A and matrix B. Let us now discuss about vector spaces. Let n be a positive integer and R is to per n the set of n tuple of real numbers, that is, a collection of elements of the form x1, x2, x3 until xn, where the xi are real numbers. We define the following operations on Rn. First, addition, that is, x1, x2, x3 and so on till xn plus y1, y2, y3 and so on till yn is equal to x1 plus y1, x2 plus y2 and so on till xn plus yn. Second, multiplication of a vector by a scalar, that is, alpha times the vector x1, x2, x3 and so on till xn is equal to another vector which has the elements as alpha x1, alpha x2, alpha x3 and so on till alpha xn. Given that small u, v, w belongs to Rn and alpha, beta are scalars, the following properties are satisfied. That is, u plus v is equal to v plus u. Also, the associative law which says u plus within the brackets v plus w is equal to the sum of u and v plus w. Also, u plus 0 is equal to 0 plus u, and which equals u itself. 0 is a vector with the all elements being 0. U plus minus of u is equal to 0. Alpha times the vector u plus v is equal to alpha times u plus alpha times v. Then alpha plus beta times vector u is equal to alpha times u plus beta times u. Alpha times the product of beta times alpha into the vector beta u is equal to alpha beta times vector u. 1 times vector u, 1 into vector u is equal to u. The set Rn with the above operations and properties is called the Euclidean space. A vector space is a set V, capital V is a set capital V together with the following operations. Addition, if small u v belongs to the vector space V, then u plus v also belongs to vector space V. Another identity for multiplication of an element by a scalar. If alpha belongs to R and u belongs to vector space V, then alpha times u belongs to vector space V. These operations satisfy the properties listed above. If in the above definition our scalars are complex numbers instead of real numbers, we obtain the axiomatic definition of a complex vector space. Examples: Rn form a vector space. Let C be the set of all complex numbers, then C to the power n form a vector space. Let M with the indices Mn be the set of all M cross n matrices. Then M with the indices Mn form a vector space. Let V be the set of all non-negative real numbers, then V is not a vector space. We will now discuss about the span of a vector. If the vector u1, u2 and so on till ul are vectors in a vector space V, then the set of all linear combinations of these vectors, that is all vectors of the form a1 u1 plus a2 u2 plus so on till al ul, where a1 to al are arbitrary scalars, is called the span of vectors u1, u2 and so on till ul. The set u1, u2 and so on till ul is called the generating set of span u1, u2 and ul. Let us take up examples. Let u is equal to 1 and 3 be a vector in the xy plane. Then span of u is the set of all vectors of the form k times k and 3k. That is, the set of all points on the line y is equal to 3x. Similarly, the span of the vectors 1, 3, 3, 9 is also the same set of vectors k, 3k. But span 1, 3 and 2, 3 is the space a1 times 1, 3 plus a2 times 2, 3 judges the entire plane. Span is always represented within curly brackets. Let us begin with the vector subspaces. Let W be a subset of a vector space V. Then W is a subspace of V if first, when UV belongs to W, then U plus V also belongs to W. Second, if alpha is a scalar and U belongs to W, then alpha times U belongs to W. Every vector space has two trivial subspaces V and the null space consisting of zero vector. A subspace of a vector space is itself a vector space. We next take up the linear independence, the dimensions and bases. Let a1, a2, a3 until am be a set of m vectors in a vector space V, and let k1, k2, k3 and so on till km be m scalars. Then k1 a1 plus k2 a2 plus k3 a3 till km am belongs to V. One solution of the equation k1 a1 plus k2 a2 plus k3 a3 plus km am is equal to 0 is the trivial solution ki equals 0 for I taking up the values 1, 2, 3 and so on till m. If this is the only solution of the equation, then the vectors a1, a2, a3 until am are said to be linearly independent. Otherwise, they are linearly dependent. If all the coefficients ki are not 0, then at least one of the vectors can be expressed in terms of the others. It implies that we could have worked with a fewer than m vectors. Second, given a vector space V, it is possible to find at least one set of n vectors which are linearly independent. But any set of n plus 1 vectors is linearly dependent, the space is n-dimensional. Third, any set of n linearly independent vectors is said to form a basis in this n-dimensional space. Let us take up some examples. First, in R cube, the vectors a1 equals 1, 1, 2, a2 equals 1, 0, 1, a3 equals 2, 1, 3 are not linearly independent since a1 plus a2 minus a3 is equal to 0. Second, in R cube, the vectors a1 equals 1, 0, 0, a2 equals 0, 1, 0, a3 equals 0, 0, 1 are linearly independent since k1 a1 plus k2 a2 plus k3 a3 is equal to 0, 0, 0, which implies k1 is equal to k2 is equal to k3 equals 0. Third, the vector space R cube is three-dimensional. Given any vector A to be equal to a1, a2, a3, it can be written as a linear combination of the above three vectors. That is, A is equal to a1 times vector a1 plus a2 times vector a2 plus a3 times vector a3. Since vectors a1, a2, a3 are linearly independent, the maximum number of linearly independent vectors is 3. Hence, R cube is three-dimensional. Since Also, since vectors a1, a2, a3 are linearly independent, they form a basis in Rq. We will next learn about the determinants. Determinants were introduced for solving linear systems but are not of much practical help. They have important applications in eigenvalue problems apart from other fields. A determinant of order n is a scalar associated with an n cross n matrix A and is denoted by D is equal to determinant of A, which equals the determinant of the matrix with the first row being A11, A12, A13 and so on till A11 and so on till A1n. The second row being A21, A22, A23 and so on till A2n, and similarly the last row being AN1, AN2, AN3 till ANN. For n is equal to 1, the determinant is D is equal to A11. For n greater than 1, the rule is obtained by induction. That is D is equal to AI1 into CI1 plus AI2 into CI2 plus so on till AIN into CIN, where I take up the value 1, 2, 3 or so on till n. Or equivalently, I can write the above expression as G is equal to A1j into C1j plus A2j into C2j plus so on till ANJ into CNJ, where j can take any value lying between 1 to n. Let us now discuss some simple properties of determinants. Cij is equal to minus 1 raised to power I plus j mij, where mij is the determinant of order n minus 1 obtained from determinant A by omitting the ith row and jth column. In this way, D is defined in terms of n determinants of order n minus 1, each of which is in turn defined in terms of determinants of order n minus 2 and so on. From the definition, it follows that we may expand D by any row or column. Mij is called the minor of Aij in D and Cij is the cofactor of Aij in D. The determinant is a sum of n factorial terms. Each term is a product of n factors. Interchange of two rows or columns changes sign of the determinant. Now, adding multiple of a row or column to another row or column keeps the determinant unaltered. Multiplication of a row or column by C multiplies the value of determinant by C. Transposition leaves the value of a determinant unaltered. A zero row or column or proportional rows or columns render the values of the determinant zero. In particular, a determinant with two identical rows or columns is zero. Next topic is the rank of a matrix. Let A be an n cross n matrix. Any matrix obtained from A by deleting certain at most n-1 rows and certain at most n-1 columns from it is called a submatrix of A. Thus, the matrix A21, matrix A11, A12, A31, A32, the column matrix A11, A21, A31 are all submatrices of matrix A given by A11, A12, second row being A21, A22 and third row being A31, A32. A matrix A, not necessarily square, is of rank R if it contains at least one R cross R submatrix with non-zero determinant, but no square matrix larger than R cross R with non-zero determinant. Follows that an n cross n square matrix has rank n if and only if determinant of A is non-zero. For example, matrix A is equal to a 3 cross 3 matrix with the first row being 5, 2, 0, second row being minus 2, 1, 0, third row being 2, 3, 0. This implies determinant of A is equal to 0. Then the determinant of the 2 cross submatrix, which is first row being 5, 2, second row being minus 2, 1, is equal to 9. This is not equal to 0. So this implies that the rank of matrix A is equal to 2. Let us study the inverse of a matrix. The role of an M cross N matrix A equals Aij form an n-dimensional vectors of which there are m in all. These are called the row vectors of A. Let us write them as R1, R2 and so on till Rn. Similarly, we have n m-dimensional column vectors C1, C2 till Cn of A. Further, we define the vector spaces span R1, R2 till Rm and span C1, C2 till Cn as the row and column spaces of A respectively. The dimensions of the row or column space equals the number of linearly independent rows or columns of A. For a matrix A, the maximum number of linearly independent column vectors is equal to the maximum number of linearly independent row vectors, which in turn equal the rank of a matrix. Given a square matrix A, if there exists a matrix written as A inverse such that A into A inverse equals A inverse into A equals the identity matrix, if the inverse of a matrix exists, the matrix is called non-singular and otherwise it is called singular matrix. It is easy to show that the inverse, if it exists, is unique. Let us take up the theorem now. The theorem states that the inverse A inverse of a matrix A exists if and only if rank of matrix A is equal to n. Let us prove it. Let A be the given n cross n matrix. Consider the linear system Ax is equal to B where B is arbitrary. If the inverse of A exists, then multiply on the left hand side by A inverse. So we get the equation as A inverse into Ax is equal to identity times x, which equals x, and in turn is equal to A inverse times B. This shows equation which states the linear system Ax is equal to B has a solution. Since the inverse of a matrix is unique, the solution is also unique. But this implies that the rank of matrix A is n. We can also do it in a converse way, where conversely, let the rank of matrix A be n. Then the solution of equation for the linear system Ax is equal to B is unique for any B. If the equation is solved by the process of elimination, then xi are linear combinations of pi. Hence, we can write x is equal to matrix G into B, where the matrix G is to be determined. So putting this back into the equation for the linear system, we get A times matrix G into B is equal to B. Since this is true for each B, so the product of matrix A and matrix G is equal to I, or D is equal to A inverse. Hence, the theorem is being proved. Since the rank of an n cross n matrix is n, if and only if the determinant of the matrix is not equal to 0, the theorem can also be stated as the inverse of a matrix A exists if and only if determinant A is not equal to 0. We will next try to understand the linear systems. A system of linear equations or a linear system models many applications in mathematics, physics, engineering, economics, statistics, and many other areas. A linear system of m equations in n unknowns is a set of equations of the form a11x1 plus a12x2 plus so on till a1n xn is equal to b1. a11 x1 plus a12 x2 plus so on till a1n xn is equal to b2, and in similar way we can write the equation am1 x1 plus am2 x2 plus so on till amn xn is equal to bm. The aij are given numbers and are called coefficients. The bi are also given numbers. If all the bi are 0, the system is called homogeneous, else it is called the inhomogeneous system. A set of numbers xi that satisfies all the m equations form a solution of the equations. The numbers xi, where I take up the values from 1 to n, together form a solution vector x of the linear system. A homogeneous system always has at least one solution, which is the trivial solution x is equal to 0. We next take up the matrix form of the linear system. The m equations, as specified in equation 2, may be written as a single matrix equation, matrix A into matrix X is equal to matrix B, where matrix A can be specified as Aij matrix, which is the m cross n coefficient matrix, X is the column matrix or column vector of solution, and B is the column matrix of the inhomogeneous terms. So, matrix A can be written as a m cross n matrix with the first row being A11, A12, A13 and so on till A1n, second row being A21, A22, A23 and so on till A2n, and in the similar way the last row being AM1, AM2, AM3 and so on till AMN. The column vector X is equal to X1, X2 and so on till Xn. The column matrix B is equal to B1, B2 so on till Bm. Note that X has n components whereas B has m components. Then m cross n plus 1 matrix, which is the matrix A tilde, is equal to the m cross n plus 1 matrix specified by A tilde is equal to the first row being A11, A12, A13 till A1n and B1, the second row being A21, A22, A23 till A2n and B2 and so on till last row being AM1, AM2, AM3 till AMN and BM. This is called the augmented matrix of the system, which is specified by the equations 2. The augmented matrix contains all the information which is appearing in equation 2. Let us take up the fundamental theorem of linear systems. First is the existence of solution. The linear system described in equation 2 of m equations in n unknowns is consistent, that is, it has a solution if and only if the matrix of coefficients and the augmented matrix have the same rank. Let us prove it now. Write equation 2 in terms of the column vectors of A, that is C1x1 plus C2x2 plus so on till Cnxn equals B. The augmented matrix A tilde is obtained by adding a single column B to A. Since the rank of a matrix is the maximum number of linearly independent columns of the matrix, so rank of the augmented matrix is either equal to the rank of A or one more than that. If equation 2 has a solution X, then the above equation 3 shows that B is a linear combination of those column vectors. Hence, A and A tilde have the same number of linearly independent column vectors and therefore the same rank. Conversely, if A and A tilde have the same rank, then B must be a linear combination of columns of A. That is, B is equal to A1C1 plus A2C2 plus so on till ANCN, since otherwise rank of matrix A tilde will be one more than that of A. But a comparison of equations 3 and 4 implies that equation 2 has a solution, namely x1 is equal to a1, x2 is equal to a2, and x so on till xn is equal to an. Hence, the theorem is proved. The second theorem proves the uniqueness of solution. It states that the system of linear equations specified in equation 2 has precisely one solution if and only if this common rank of A and matrix A tilde equals n. We will prove it now. If rank of matrix A is equal to n, then the n column vectors in equation 3 are linearly independent. In that case, the representation given in equation 3 of matrix B is unique. For if this representation is not unique, B is equal to C1x1 plus C2x2 plus so on till Cnxn, which equals C1x1 bar plus C2x2 prime plus so on till Cnxn prime, which implies C1 into x1 minus x1 prime plus C2 into x2 minus x2 prime plus so on till Cn into xn minus xn prime is equal to 0. That the columns Ci are linearly independent implies that x1 is equal to x1 prime, x2 is equal to x2 prime, and so on till xn is equal to xn prime. Hence, the theorem of uniqueness is proved. The theorem implies that m must be greater than or equal to n. For if m is less than n, then the rank of A cannot be more than n and therefore must be less than n. The third theorem proves that the infinitely many solutions. It states that if this common rank of matrix A and matrix A tilde is R, which is less than n, then the system of equations 2 has infinitely many solutions. All these solutions are obtained by determining R suitable unknowns whose submatrix of coefficients must have rank R in terms of the remaining n minus R unknowns to which arbitrary values can be assigned. In this case, we have an n minus R parameter solution. We will prove it now. If this common rank R is less than n, then according to the theorem on rank of a matrix, the matrix A has only R linearly independent columns. The rest n minus R can be written in terms of linear combinations of this set. Renumber the columns and the unknown xi and denote them by a bar, so that the linearly independent set S is given by C1 bar, C2 bar and so on till CR bar, and equation 3 takes up the forms C1 bar x1 bar plus C2 bar x2 bar plus so on till CR bar xr bar plus CR plus 1 bar xr plus 1 bar till Cn bar xn bar is equal to B. The vectors CR plus 1 bar till Cn bar are linear combinations of the vectors of the set S, and so are the vectors xr plus 1 bar into CR plus 1 bar till xn bar Cn bar. Express these vectors in terms of the vectors of S. Collect the coefficients of the various vectors. Let these coefficients be y1, y2 and so on till yr. Then C1 bar y1 plus C2 bar y2 plus so on till CR bar yr is equal to B. Each Vi, which is equal to xi plus ai, where I take up the values going from 1 to r, where alpha I is the contribution coming from xr plus 1 bar into cr plus 1 bar till xn bar into cn bar. Since the system specified by equation 2 has a solution, these Vi satisfying the above solution exist. Further, since S is a linearly independent set, these Vi are unique. Choosing xr plus 1 prime till xn bar fixes the ai, and corresponding xi bar is equal to yi minus ai, where I take up the values 1, 2 and so on till r. These theorems apply to homogeneous as well as inhomogeneous systems. We'll first discuss about homogeneous systems. From the fundamental theorem just proved above, we have the following theorem for a homogeneous system. The theorem says, given the homogeneous system a11x1 plus a12x2 plus so on till a1n xn is equal to 0, a11x1 plus a12x2 plus so on till a1n xn is equal to 0 till am1x1 plus am2x2 plus amn xn is equal to 0. First, it always has the trivial solution, which is x1 is equal to x2 is equal to so on till xn equals 0. Second, non-trivial solutions exist if and only if rank of matrix A is equal to R is less than n. Third, these solutions together with x is equal to 0 form a vector space of dimension n minus r, which is called the solution space. We will prove this theorem now. First part, B is equal to 0 implies that rank of matrix A is equal to rank of matrix A tilde. Hence, the system is consistent. If rank of matrix A is equal to rank of matrix A tilde is equal to n, then the fundamental theorem implies that the solution is unique. But x is equal to 0 is a solution, hence this is the unique solution. If rank of matrix A is less than n, infinitely many solutions of which one is the null solution. Now the third part of the theorem, let x1, x2 be two solutions of equation 5, then A times matrix x1 is equal to matrix A times x2 is equal to 0. Then so is alpha 1 into matrix x1 plus alpha 2 into matrix x2. That is matrix A into alpha 1 times matrix x1 plus alpha 2 into matrix x2 is equal to alpha 1 into matrix A into matrix x1 plus alpha 2 into matrix A into matrix x2 is equal to 0. Hence, the solutions form a vector space. If rank of matrix A is equal to R, which is less than n, then the part 3 of the fundamental theorem implies that we can choose suitable unknowns. So we can call them xr plus 1 and so on till xn in an arbitrary fashion, and every solution is obtained in this way. Hence, a basis for the solution space is y1, y2 and so on till yn minus r, where the basis vector yi is obtained by choosing xr plus I is equal to 1 and the rest 0. The corresponding first R components of this solution vector are then determined. Thus, the solution space of system specified in equation 5 has dimension n minus r. Hence, the theorem is proved. For a homogeneous system, if x1, x2 are two solutions, then so is any linear combination. This is not true of the inhomogeneous system. The solution space of the homogeneous system is also called the null space of A because Ax is equal to 0 for every vector x in the solution space. Its dimension is called the nullity of A. Hence, the above theorem states that rank of A plus nullity of A is equal to n. By definition of rank, rank A is less than or equal to m. If m is less than n, rank A is less than n. By the above theorem, this gives the practically important theorem that a homogeneous linear system with fewer equations than unknown always has non-trivial solutions. If the homogeneous system described by equation 1 is consistent, then all of its solutions are obtained as x equals x naught plus xh, where x naught is any solution of system described by equation 1 and xh is the set of all solutions of the corresponding homogeneous system. Let us prove it now. If x naught is a given solution of equation 2 and xh is a solution of corresponding homogeneous equation 5, then A times x naught plus xh is equal to A times x naught plus A times xh, which equals B plus 0 and is equal to B. Hence, x naught plus xh is also a solution of system 1. On the other hand, if x and x naught are two solutions of equation 1, then A times x naught minus x is equal to A times x naught minus A times x is equal to B minus B equals 0. Hence, every solution of equation 1 can be obtained from one of its solution and a linear combination of the solutions of homogeneous system. Let us now discuss the Cramer's rule. Cramer's rule is a method of finding the solution of linear equations in terms of the matrices of coefficients. The rule is not of much practical importance except for a system of only few equations, but is of some theoretical interest. The rule states the following. First, consider a system of n equations in n unknowns. That is, a11x1 plus a12x2 plus so on till a1n xn is equal to b1. In the similar way, the last equation can be written as an1x1 plus an2x2 plus so on till ann xn is equal to bn. If the determinant of the coefficients aij is non-zero, the system has a unique solution. Second, this solution is given by the Cramer's rule, which is x1 is equal to d1 by d, x2 is equal to determinant d2 by d, and xn is equal to determinant dn by d, where di is the determinant of the matrix in which the ith column of A has been replaced by the column B. So students, let us now summarize what we have learned in this module. We introduced the idea of matrices and stated their importance in various branches of learning. Then, we defined some simple matrices of interest. Next, we introduced certain operations on matrices, including matrix multiplication. Then we introduced mainly real vector spaces, span of a vector, linear independence, dimension and basis for a vector space as a prerequisite for studying linear systems. After that, we defined determinants and described some of the simple properties. We defined rank of a matrix and inverse of a matrix in terms of determinants. Next, we introduced linear systems. We state and prove the fundamental theorem of linear systems and apply it to homogeneous and inhomogeneous systems. Finally, we describe Cramer's rule for solving linear systems in terms of determinants. Thank you, students, for your attention.